Good. So, I'm Adnan Boss. I actually know some of you guys. So today, we're gonna talk about thinking in parallel. Presentation I gave in HPC and GPU supercomputing group of South Florida. I'm actually the organizer of this group. You see currently the logo on the screen, and this group is sponsored by NVIDIA, and we have many groups like this all over the country, actually all over the world. There are also some in Tokyo and other places. So let me ask you, can you hear me well? Can you see the screen well? Everything is okay there?
Yes.
Yes? Great. Alright. Now, HPC and supercomputing groups, as I said, these are NVIDIA sponsored, and all of them are actually on www.meetup.com website. And if you go there, you can see there are many supercomputing groups with the same name but different city names, like South Florida or California or New York and many others. And these groups started in 2011, the beginning of this year. Currently, we have actually more than 1,000 members all over the country, and it is increasing very fast. And the reason of these groups is to provide supercomputing technologies to show everybody that supercomputing isn't just done in academia or in bigger companies, but you can do supercomputing even on your desktop computer or on your laptop. So you can see our activities. You can also join our group. You don't have to join our meetups, but you can join our groups because we always put out the material we present in the presentation. You can download some presentations or talks from there. And today's meeting is thinking in parallel. It is in Russian. Sorry, I don't know Russian, but I pasted here. I hope I pasted the correct wording, right? Parallel. I can read it also. So, and thinking in parallel is a presentation I gave before in couple meetups and also in Florida.net user group. And today I would like to share it with you. It's a stuff to get, to stay in touch with the latest technology advances. So the thinking in parallel term is the conceptual, making the conceptual leap that takes the developer from writing programs that have little or no parallelism to start writing programs which work in a massively parallel hardware. And as I said, massively parallel hardware doesn't mean a supercomputer at the school or at your work, but could be a supercomputer on your desktop or your laptop. So today's presentation topic is all about this. So I'm going to start with a quote from H.G. Wells, and it says, in this precious file is a powerful thing twice as fast, move twice as quickly, do twice as much work in a given time as you could otherwise do. So this is the whole idea. You have some resources, and until now you were doing certain stuff at X amount of time. Now you will be able to do the same task in much shorter time. That means much faster. This is the whole idea behind thinking in parallel. And the new accelerator, this is the book from H.G. Wells. It's definitely not about computers from 1901. It is more about somebody invents a special potion to make people faster, but it exactly fits our current goals with thinking in parallel. Let's step back and look what parallel means and serial means. As you know, most of the programs today are serial. So, and serial is traditional. Actually, this is the way your brain also thinks. You cannot think in parallel exactly. We always think step by step. We do one task, then we do the second task, then we do the third task. So everything is sequential, and it is really easy to think. And let's give an example about how we think or how we compute actually in sequential logic. Most probably everybody knows already there, but here is a prefix sum. It's a scan algorithm. It is used on many algorithms like sorting or searching or more complicated algorithms. Very basic algorithm, prefix sum. So given an array of 5, 1, 8, and 11, if you run a prefix sum on it, sorry, the prefix sum of it. And here in this example, you end up with 25. It's a very small array, just 4 elements. But think about you have millions of elements in it, and you have to sum it. If you go in a sequential way, it is really slow. You really don't utilize your computer hardware. So, for example, a code would look like this: for all I from I and 1 to n. So you would just add it up. It goes very sequential, very straightforward. And now, sequential thinking, actually sequential computing is going to change. We can see this all around our community in the last 10 and 15 years, And you may heard about Moore's law. So according to Moore's law, it was always doubling every year. Now it's just not much doubling anymore. It dropped to 20% in 2002, the old graph. But nowadays, it's really flattened. It doesn't go up anymore. And that means you cannot squeeze much power out of sequential computing or single core or single CPU operation. So that means from now on, everything is going to software programming is going parallel. And sorry, yeah. So if we say everything is
sorry.
Right.
May continue.
All right. Then we say
guys, hold on a second. Since there's a pause, how's everybody understanding the content? Как понимаете, то есть нормально, проблем нет с тем, чтобы понимать, как одно говорить?
Ну, я не самый, наверное, ну, я не хорошо достаточно понимаю английскую речь, но одно я понимаю, в принципе, нормально по слайдам. Особенно, когда есть текст, я понимаю. То есть, когда он говорит и объясняет.
Alright. Alright, Mr. Boss, I just asked if everybody understands well, sorry, everybody is cool. I think everybody understands you well.
Great. I can talk a little slower or try to make it more clear. Because it is morning here, actually, my jaw is kind of tired and actually not opened up. Therefore, maybe I'm swallowing some words. Okay. Now, we said multi and many core computing. Actually, now we're saying multi and many core computing hitting the mainstream. That is the logic of everything is going parallel. So when we look at the current industry, we see that today we got 4 and 12 cores, and in a few years we will have 32 cores, and Intel actually is predicting that in 2015 we will have at least 100 core machines on our desktop. Intel had conference about a month or 1 month might actually see that when you go to Intel's website, they talk about it, and also you can see the trend that there is not much increase on the CPU speed anymore. And if you look to other companies, it's the same thing. For example, AMD has 12 core today, Sun has 16 core, IBM has 8 core, 12 core on Intel. So the PlayStation you're using has 9 cores. NVIDIA has 1,000 cores, actually 1024, and there are other technologies, specific technologies like Adaptiva has 4,000 core on a single device, and other also has many cores. I googled actually who has how many cores on the CPU. Even on Wikipedia, you can get a list of multi-core, many-core machines, and it is obvious that it's going to be more and more. This is on the hardware side, and on the other side, operating system and compilers and debuggers. Actually, we see also a huge list of applications and support for parallel computing. And even in 2008, there was somebody made a list how many parallel languages, programming languages we have, and it is more than 100 programming languages, and nowadays it is hundreds of them. Here I listed a couple tools and technologies you can use to do parallel computing. This is Microsoft Path Parallel Library, Intel's threading building block, TPL you may know, it's in .NET. Then Parallel Virtual Machine, Pthreads from cWorld, TLink, OpenMP, really pushing towards running massively parallel applications on your computer. So C++ AMP, what it does, it utilizes your GPU just with a couple commands. You don't have to really write huge applications like any GPU hardware. That's really good technology from Microsoft just came out. NVIDIA couldn't see it is the main technology actually we are supporting, we are promoting in our user group. It is a language, it's a library on top of actually C. There is a compiler also. It gives you the power to do supercomputing on NVIDIA GPUs on your desktop. So ATI has also another library. ATI is not the leader on using GPUs for computation on your desktop, but they are also trying to follow it. There are other technologies, open source like OpenCL and Brooks and many other. Microsoft on the other side has also this direct compute technology. You may have heard about it. It is based on direct 3D. So if you have a graphics card, doesn't matter ATI or NVIDIA whatever, or even Intel, you can run direct compute to utilize it and make data calculation on your GPU instead of graphics processing. And now, as I thought, the hardware part and the software part is keeping up. Every day there are new software, there is new hardware, and soon we will have these hundreds of cores on our desktop right under the box. Now, what are the problems? What are we going to face? Even if they have a huge code base developed with little or no parallelism. Think about it. I don't know, Office or any big application you can think about which is widely used, and it doesn't use parallelism. Now the company has to go back and change this 1 million lines of code and convert it to work on multi-core system more efficiently. And in order to add new features, or keep up with competitors, the companies really have to go this route, because the hardware will not allow higher speeds on the CPUs anymore. Another issue, we really haven't been teaching much about parallelism for many years. In years especially, most students in the last 10 years know just a little about parallelism. The whole logic is about how the sequential computing is working, how the sequential logic is working. That's why engineers today have to understand how parallelism works, understand all the issues and of the parallelism, and need to know how to utilize all the cores in a machine. And parallel thinking is really not the latest API library or hardware. Parallel thinking is a set of core ideas here to identify and teach everybody and to understand and learn about it. So this presentation is actually giving you insight how you can change your mindset or thinking approach in order to adapt yourself to the new upcoming technologies. So this graph shows more details about the situation. So writing with serial hardware is, hard. You have to make sure it is working good, it doesn't work easy. But there is a trend in our industry. After 2004, this line is 2004, we name it single core era, and after 2004 we name it multi-core era. Now, before 2004, if you were writing a software, it was automatically running faster the next year with a new hardware, right? We had 1 gigahertz, 1.2 gigahertz, and the next year it was 2 gigahertz, and suddenly everything was running faster. So that really stopped at 2004 because the computer started getting more cores, dual core, quad core, instead of getting more horsepower. And we can say, if you continue writing serial applications, you will never utilize the hardware potential here. This is the real hardware potential. And there is a competitive market out there. If you want to really catch the competitive market and compete with other companies or with other developers, even if you're looking for a job to write applications which is performing very well, you really have to catch up, and it really matters where you stand in this line, how much parallel applications you're writing. So it's utilizing the full hardware potential. And I can show you here how parallel thinking works. Now we talked about serial prefix sum. If you run the same prefix sum or the other name is scan on parallel, it would look like this. This is the main logic. So instead of summing sequentially this one number to the other, one number to the other, you will end up with this chart. On this chart we have 16 numbers. This is a 16-element array. The first step. Second step, you will take the result, send it to 4 cores. Next step, you will take the result to send another 2 cores, etc. You can actually run this in parallel. You can run it on 16 cores if you will scroll these up. This will be a little crowded, therefore, if you have to separate it out. You can really run this in parallel and until this point. So there is an example about parallel prefix sum on NVIDIA website. I put it in tiny URL of it. So it shows you how you can do this kind of tenfold or 100-fold faster. It is incredible how you can run it really fast. The problem, though, maybe this example doesn't sound very interesting or very common for you, but most of the algorithms use prefix sum. Even if you do today some kind of sorting, you end up using this in a very deep algorithm. Now, where to start? I put here together a couple of books, and these books are really good, and they have different flavors. Actually, they explain different aspects of the technologies. And there is a book named The Art of Concurrency. This is not a very new book, but it tells you what is really parallelism. It may say concurrency, and I will come to that, what concurrency means and parallelism is. But it gives you very good insight how you should change your programming logic from just parallel to serial. Then there is program massively parallel processor. This is a pure NVIDIA book, and it is based on NVIDIA CUDA technology. It is NVIDIA's massively parallel computing library you can use on NVIDIA graphics card, and it explains, it teaches you actually how you can develop using NVIDIA GPUs. Then we have the patterns for parallel programming, and this is very similar to Gang of Four book. It explains the patterns. It doesn't have any coordinates, and honestly it's boring, but it tells you all the patterns what you can really apply while doing parallel programming. And believe me, it is really, really different. You cannot count as quantity common sense. It gives you really insight how you can use parallel programming. Another good book is An Introduction to Parallel Programming. It doesn't have anything to do with GPU programming or GPU programming, all the possibilities in the parallel programming world. So if you design a supercomputer, or if you just want to spawn 16 instances on Amazon, or it tells you how to distribute a given task to multiple computers and what kind of technologies you can use. There are good samples. I think about OpenMP and other couple parallel libraries. That's also very good book. And now I want to clarify something about concurrency and parallelism. When we say concurrency, sometimes we mean parallelism, but they are really different terminology. And just to clarify the terminology, concurrency is a programming issue. You have really only few amount of these hardware resources, and with concurrency, what you do, you share these hardware resources with your program. So what you do, let's say you have only running one core, so you run your first thread for task A, then you stop running it, then you run thread 2 for task B, and back again. So you switch it. Even if you have 4 cores, you can span today, let's say 8 threads, or any thread you want. You can even span 16 threads, but it doesn't mean they will run at the same time, same exact time. It's just the hardware or the software does the magic, and it's just switching, the thread switching. It switches from one to another. So it's usually on single processors. You can have it multi-core. The goal is running multiple interleaved threads. That's the whole goal. And as you know, only one. So just talking about you have 1,000 cores. There is no issue with sending 1,000 tasks to 1,000 cores. You just span, here's the example, you span 2 tasks and they run at the same time. You can span 1,000 tasks and they will run 1,000 at the same time. There is some taxonomy about the architectures you may have seen before, or you may be using it but you don't know. Today, what you're using is usually SISD. It's single instruction, single data. So you have piece of data coming in. There is a piece of core or machinery which can calculate this data or do some operation, and you get the result. There's another type of technology which is single instruction, multiple data. So you can have 4 data coming in at the same time, 4 amounts of data, and you can have 4 processing units which processes the data at the exact same time. And I'm going to show what the multiple instruction, multiple data. It is most of the supercomputers today are based on this infrastructure, this architecture. You can have multiple data coming in, and multiple processing units can operate that data in multiple different ways to the same data. So MISD is not very used. There is actually even no example. And the main difference that we're talking about here, especially in NVIDIA, is the difference between SISD and SIMD. So this is your classical CPU when you think about it. and SIMD is GPU hardware or a hardware which has many, many cores. You get one instruction, many data, and many results. This is the main difference. And by many, we really mean thousands of thousands. SIMD is also implemented in some Intel architecture. You can actually run some interrupts directly on the CPU, which does SIMD. I actually have a couple of samples on my blog. If you visit it at my name, adnanboz.com, so you will see there are a couple of SIMD on CPU or on GPU examples. So until now, anybody has questions? Or is it clear? Should I explain clear?
1 second. Clear. All okay. All understands you.
Everyone still awake? Nobody sleeping? I can see the crowd though. Yeah, maybe we should take the camera to the crowd.
No questions.
No question, nobody sleeping. Good. So in parallel programming, we have also methodologies. And methodology is very similar to your daily programming logic, actually. It is you start analyzing, you design, you code, you test, you have a test cycle, then you measure, you may design again, it doesn't work well, then you proceed to it. The difference of parallel programming is that you really have to spend lots of time on testing and coding, actually measure, test, code, because you can gain some performance once you write the parallel application. Let's say it's working 2 times faster, but it doesn't mean it is the fastest. Sometimes, not sometimes, actually on most of the NVIDIA presentations, they run a sample application which is 5 times faster than the CPU version. Then they make small tweaks here and there based on the hardware, based on the CPU situation, and it suddenly starts working 20 times faster. So if you want to write high-performance applications, you really have to know the hardware and test a lot and actually measure a lot. That's the main idea about it. And when we say parallelism, you may think, how we start writing parallelism. At the beginning, actually, you have to analyze the parallelism. So this is the first step you're analyzing. And when we mention about analyzing, there are known rules, known laws. You don't have to invent something. It is actually pretty easy. But if you just look at these laws, it gives you some idea. For example, there is a law named Amdahl's law. This is the famous law in the parallel world. It says if you have a fixed size of problem, that is the main keyword here, fixed size of problem, and whatever you do, if your parallelizable part is not big enough, you will not get as much speed as possible. So let's say this is your application, okay? The whole thing original. And let's say the red part is the stereo logic, which you cannot parallelize for some reason. Your software doesn't work like that. And let's say the blue part is the parallelizable part. And if you can parallelize something 100%, we name it embarrassingly parallelizable. So what it says, if you just parallelize the whole blue part just until this point, look, your application actually didn't get 10 times more speed. It just improves this 20% and slows it down to 5%. At the end, you may end up just a couple times faster. On the other side, let's say this is your application, and the red part is the parallelizable part, but the blue part is the sequential part. If you will parallelize it, let's say until this point, you will get much better results. And this graph actually shows the result. So it also depends how much of your application you really can parallelize. If you can parallelize 50% of your application, which is the blue part, look, after 16 processors or computers, whatever you use, processing unit, there is even no meaning to add more. Even if you add gazillions of computers, it will not be faster because you already hit the curve here. It cannot get. Look, you can parallelize it up to 20 times, up to 4,000, maybe 2,000 cores, 2,000 computers. And after that, it also doesn't make sense. The last 5% is never achievable. Therefore, you just stop here. Amdahl's law is a good presentation. What you will get after you, let's say, refactor your code or introduce parallelism to your code. And it also shows how important it is to keep the sequential part smaller and keep the parallel part bigger. But there is also another law, which is Gustafson's law. And Gustafson's law says the problem size is not always fixed. So the problem size can get larger and larger. And when the problem size gets larger, you can really achieve and scale in a linear way your solution. And this is the graph of Gustafson's law. As you can see, as many cores as you add, it's just linear, as much speed up as you get. This is what we see actually today in my job. I'm working in a company where we do click advertising. So if somebody clicks on an ad on the internet, it goes through and we count it as a one, then we run analytics on it. And we are actually currently hitting 1 billion unique users, and I think 7 billion regular users a day, 1 billion users a month, and 7 billion a day. And that means you have to really calculate every click. And if you think we had only 100 users, we could really achieve certain amount of parallelism. Let's say only 50% is parallelizable of our application. We could not get it better than 50%. But the data is growing now. When you hit billions of users, actually that means you already speed up billion times, right? Or at least half billion times. So if the data is growing, you will also start gaining much more speed. That is Gustafson's law. These guys actually have opponent ideas. If you can check it out on Wikipedia, it's really funny. And we have also, as usual, design patterns. So as in software design patterns, we have parallel design patterns. And I'm not going to go dive into much, but I just going to mention it. And you can find this in the patterns book I mentioned at the beginning of the presentation. In just very high level, in the 300, 400 pages book, I put it in 4 sections. It first explains finding concurrency, how you can find concurrence or parallel, actually, not exactly concurrency, parallel points in your application and see, oh, I can fix this part or make it better. Then it talks about what kind of algorithms you can squeeze out of it, what kind of algorithms you can use it, and applying this algorithm, and how you can implement these algorithms. Because not every algorithm suits well to parallel programming. For example, if you want to sort something, you don't want to use quicksort on multi-core devices. You may want to use something like radix sort or other type of sort. So algorithm picking is also very important. And a little deeper into the design patterns, you end up seeing task decomposition pattern, data decomposition pattern, where you actually split everything to tasks, or you can split your data into multiple parts, data flow decomposition, and as you can see, there are many standard ways to do certain stuff, especially fork join, which is very known. I think TPL has a functionality like that. For example, if you run parallel for each, I guess at the end there's an option to join it. So that's a fork join algorithm they use there. And fork join pattern they use in TPL and Microsoft. And then I just show you 8 very high level rules. Actually, after getting into this area, you figure out easily it's not alien science. And the important thing is you have to really identify independent computation. So what are your tasks totally working independently? Then second, it is good to do parallelism on highest level. Okay, if you have 10 computers and you can span 10 computers at the same time, that is good parallelism because you spread the work towards 10 computers. Instead of, you could actually write parallelism in your for each loop, you could span one thread again and again. That is actually not a good parallelism. So keep it as high as possible depending on your problem domain and also your solution. And you also show type parallelization in libraries. So if you have parallelized version of some part, put it into a library, and you can also keep the non-parallelized and serial part for double checking if the result is correct or not. So therefore, it's good to keep it in a separate library. And you have to also use the right programming model. That's also very important. And there are many points here, but the most important point, I guess, is be pragmatic. So it is actually, if it's not reasonable, don't do it. If you have to serve or run a service, let's say it doesn't matter, it can run in 10 hours, there is no reason to run it parallel, right? But if you have a high performance situation where you have lots of data, you have to really run a lot of things instead of throwing in 3 servers, maybe you can just throw 1 server and run it in parallel. So you have to think pragmatic. There is actually thinking approach. You can think bureaucratic, you can go really detailed, or you can not think anything, it could be chaotic, but pragmatic is the best thinking approach. It's just good enough. So is it good enough, or do we have to really go insanely to the other side, to the bureaucratic part? That's the main idea. And I walked a list of a couple of technologies I mentioned at the beginning of the presentation. Maybe now it will make more sense for you. Maybe you already used it. Microsoft Task Parallel Library. It is the library where you do parallel, actually it's a system.threading.task namespace. You do parallel for each or parallel for. It is underneath, it is using all the parallel patterns, and you can do many good things there. It actually hides all the complexity of the threading. It still uses the thread queue, regular thread queue, but if you're multi-core, it will take definitely advantage of it. Intel threading building block is on the C++ world. It's also a nice library. And MPI is a message passing interface. It's a standard, actually. There are many tools or many libraries which is doing that. It is the most known technology for supercomputing to communicate two nodes, two processors, two computers between each other. And you can really achieve high performance on this. And there are many other technologies on the CPU side, like MS, C++, AMP, Microsoft's latest and greatest technology they announced recently. And concurrency runtime is TPL on the C++ world. So it's the same thing. And it provides very similar functionality like parallel for each or other things. On the GPU world, actually that's what we are promoting usually. We have the NVIDIA CUDA C. And as I said on our website, supercomputinggroup.com, we have a couple presentations about it. I give a couple presentations on it. And you can also access many resources about it. So it gives you the option to separate some high performance required logic into some CUDA C language, and after you can run it really fast on GPUs. Then ATIS, similar technology. Microsoft is trying to catch up with direct compute, but now they shifted to C++ AMP, and AMP is also working with DirectX 3D to run GPU computing. Then Brooks shaders, PGI, the CUDA is a Fortran version, and GPU.NET is actually a CUDA wrapper for .NET. You can also use it. It allows you to do GPU programming through .NET environment. And we have also Trust. Trust, I have one full presentation about Trust. Trust is a very good technology. It's a high-level library on top of CUDA-C. So in Trust, you may say just sort and it's ordered by the best algorithm on the GPU, or you just multiply the whole array with a number and it does it on GPU, but you never see the complexity. It's just hidden behind. So those are our technologies. And those are links and references, guys. Any questions? And I can send this presentation to you, so you can look at the links and references, and I will ask for questions and answers.
Do you have a question? Hi Adam, it's Andrei. I have a question to you. Which developer tools do you actually use in your work? Which ones from your list?
I'm using TPL, MS Concurrency Runtime, and NVIDIA CUDA-C, and Trust. Yeah.
Okay, thank you. That was just interesting. Thank you.
Yeah, that is now on the GPU world. You want to really pick a technology to utilize your graphics card, and these are the options. And we tried Microsoft Direct Compute, but after a while, I figured out you cannot make Direct Compute work without having a monitor plugged into your graphics card. And we don't want to plug monitors to 10 graphics cards running on a server. So that's why I had to eliminate Microsoft Direct Compute and to return to CUDA-C. This is a very good technology. On the CPU side, TPL actually uses every day. On .NET applications, it's not so common. We don't directly spam JS anymore. We just say, okay, start new task. This is a factory class, or just parallel for each from the task library. This is very common. And MS Concurrency Runtime, it's used for C++ because this is C++ part. We don't have TPL for .NET. So this is the equivalent on that world.
Arnold, this is Alex. Can I ask you a question as well?
Sure.
Since you were describing the technologies for the parallelism, link is used a lot, and there's a parallel link technology. You did mention that technology in a frequently used list. That might be because of link is actually and not a direct technology, it's an indirect technology based on data access, and C-link might be even more heavyweight technology. So is that correct? Do you agree that the C-link is kind of not very optimal, and that is the reason, and lots of wrappers, and therefore you did mention it in the list of technologies you use?
So we don't use C-link because in my world, in my company, actually maybe other people use, but not on my project, because we usually do backend software. We don't access database much. We access Algo, and for collection operations, we usually have our own algorithms and run on this is very Go algorithms. LINQ is very high-level language. It's just powerful. It gives you lots of flexibility, and whoever is using LINQ should be able to use TLINQ easily. I believe I didn't use TLINQ before, but it is really the way you go. When you write LINQ, you should not just drop LINQ and call to Intel CDB or something like that. So there are supporting technologies as TLINQ. Definitely, TLINQ is something to use. So all the technologies are really great technologies. You can use it. So yeah, I don't use it in my project because I have really few LINQ queries on some dictionaries, on some collections. That's why I didn't use it. Microsoft has this Dryad actually. This is, I don't remember now exactly. I read about a couple of months ago. I would suggest you to check it out. It is based on LinQ and utilizing GPUs, something like that. I don't remember exactly. It was really interesting technology. It should be still on Microsoft released it, I think. And it's really nice technology.
Can I ask one more question?
Sure.
Since this is an introductory presentation, what are the differences in deployment and in development in IDE environment and in deployment for when you program when you work on parallel programming using the GPU?
You mean how it is deployed, or what are the challenges on deploying it, or?
Yes. What are the notable differences in your development environment IDE and in your when you develop and when you push to deploy? Because we usually in traditional programming, everything runs in CLR, and I don't know what's the situation here. Do we have anything special to do in deployment?
I see. Yes, we have a development environment here. First, you need if you do GPU parallelism, you need the GPU, that's for sure. But everybody has a graphics card today. So then you have to install these special libraries. Like if you want to go with NVIDIA, you download from NVIDIA website and you just install it to your computer. It automatically actually installs all necessary things into your Visual Studio. So it has full Visual Studio integration. And on my blog, actually, I give examples starting from scratch how you can install and use it in Visual Studio. It's really simple. Then once you get that done, you have to start using this library. You have to include this library into your project. If you write NVIDIA CUDA-C, you really have to write it in C++. But again, on my blog, I also show you how to write a wrapper for the code you just wrote for GPU and utilize this library or use this library in your .NET C# application. It's really simple. It's not really hard. And if you use another technology like they use GPU.NET, the only thing you have to do then is install GPU.NET and after include the reference to the .NET CLR, and it should work as it is. On deployment, you have to deploy the runtime library. That's the only requirement. So what you have to do, you deploy it with all the compiled DLLs and pass the runtime library of CUDA, for example, if you use CUDA. And other than that, nothing is required. It starts working. If you use actually today any NVIDIA card on your computer or on the server, you can utilize any of them to calculations. And you can check your graphic card performance or the capabilities online, what you can do and what you can't do. So it's really not hard. The thing is, there are some challenges on deploying a production environment if you have really big bandwidth of data. It's just you have to buy a good hardware. You cannot just go with a $100 graphics card. You can write your whole application on a $100 graphics card, and it will definitely and guaranteed work on the production because NVIDIA guarantees that the same language we use will work on the next graphic card or a bigger graphic card. But the problem is you don't put the $100 graphic card to production. You really have to buy something more robust, more high-performing. Let's say an NVIDIA series, there is the M-series graphic cards, M2050, I guess. Yeah, there's S1050 and M1050. So these, if you put that, it costs $3,000, but it gives you, let's say, 500 cores. It gives you 6 gigabytes of memory. And at home, if you buy just one of those graphics card, it has only 32 cores. It has only 500 megabytes of memory. And it also will break actually if you run it every day and for a year or many years. So the server cards are different worlds. And it's the same as running a production server. When you run a production server, you don't just throw a $1,000 server. You go and buy a good Dell server or whatever server, which costs $10,000 because you want to make it behave good. On the other side, production is not just limited today to custom hardware. And if you go to Amazon search, actually, there are EC2 instances which you can span on GPU. Until now, until last 3 months, they had only Linux instances for GPUs. Now they have also Windows 2008 R2 instances for GPUs. So you can just span in Amazon Cloud, couple servers, and you can run whatever you want to run there. I think $2.5 an hour, and more expensive than the other ones, but it works. I hope this answers the question. Any questions, guys?
Hello? You told us that we can only improve the part of the software that can be parallelized. But what would you recommend to do if a program performance is limited by the hard disk or SSD disk? For example, if you have a program that needs to process a lot of data, for example, several terabytes, and data reads slower than all processors process it, and they cannot hold all the data in memory. Even 6 gigabytes isn't enough. What does theory of parallel programming recommend to do in such situation?
Okay, the question is, what if we have I/O bound, we name it I/O bound application, which is more I/O related work than CPU or memory related work. So, which will serve you that. But if you have really high I/O bound operation, then that means there is no meaning to throw in more cores or CPUs because it is not CPU bound. You throw in more CPUs if your operation is really CPU bound. And if you have a I/O bound operation, then you have to throw in more hard disk or distribute your hard drive. And that's a totally different solution. Like they sometimes create these arrays of disk, or you can separate it to multiple computers. This is totally different supercomputing aspect, where there are a couple technologies. Actually, there are many technologies, because today supercomputers are also using shared drive. On parallel programming, it explains very well these differences. There is also another book named MPI. It also explains how it works. So what they do, they use distributed memory. They name it memory, but they distributed storage actually. So you have a big array of disk or a big array of memory at the same time you can use, and you try to use that shared array of disk from multiple computers. If you end up in concurrency problems, then you may choose a shared nothing architecture. There are many architectures. One is shared nothing. So in shared nothing, for example, you have many computers, enough computing power actually, which is enough disk space, but they don't share anything between each other. They don't know what's on the other side. So then you have to create some higher level logic which can decide where to access which data or what to run. It's a supercomputing issue, what you're talking. It's more like about the I/O.
Okay, thanks.
Did that answer your question?
Понятен был ответ.
Вполне.
Okay. Hello. I've got some practical questions related to your work. Can you describe maybe some tasks which you successfully solve using the NVIDIA technology now, if it is not a commercial secret, of course?
Sure.
Which algorithms? Maybe some acceleration of databases process, or the algorithms of searching, or which kind of algorithms?
Ребят, можно сделать небольшое замечание? Перед тем, как вопрос задавать, если бы вы представились, потому что мы не видим, кто, и было бы лучше, если бы отдельно это изучало.
Okay, I'm sorry. Let me introduce myself. My name is Alexey Medvedev, and I've been working with parallel programming for long, with numerical programming, and actually I work now a lot with the CUDA technology, with NVIDIA technology.
Oh, great.
Okay.
So we have a CUDA fellow there. Hi.
Hello.
Now what we are using is actually a couple of algorithms. We have in couple places, and one of them is we have to match some data. We have to take two data sets and match them. That is one place we use. So what we do, we load enough data into the GPU memory, and then we run the kernel we name, as you know, and that does the mathematics on the data. So it goes through the whole data set and matches and creates a result set. That's one place we use. Another place we use is building a special data structure we name Bloom filters, and it is to make the data set smaller. If you have lots of IDs, let's say, or some text values, you wanna maybe you can't fit into the memory, you actually use the Bloom filter logic to keep them in bits instead of just 8 bytes. So that's another part. So if you run this through the GPU actually can switch on bits or switch off bits in the memory much faster than CPU does, because we are talking about it processes about 400 gigabytes of data, and it has to process very fast. If you think about 400 gigabytes processed, 400 gigabytes long of bits processed by a CPU, it takes 12 hours or 13 hours. And if you do it with the GPU, I can spawn actually millions of threads at the same time, which it just utilizes 400 cores. So, but it does it actually 100 times faster, much faster.
Okay, and do you use multi-GPU configuration, or you do everything on single GPU?
It's a multi-GPU configuration. NVIDIA has a box for GPU in one box. There is a solution. Actually, Dell has bigger solutions, but NVIDIA's box is tested for high performance plus for durability. So it will work for a long time. It doesn't shut down, or it doesn't go bad, or it doesn't break. Because in production environment, the biggest problem is when your server just dies, something goes bad.
Okay, thank you.
So we have some CUDA enthusiasts over there too. That's great. So you guys wanna open a HPC and supercomputing group of Tula or Russia?
Actually, I don't know about the supercomputing groups like that, but what we do here in Tula, we started teaching parallel programming in our local university here, and this course is now based on CUDA technology as the most promising and most maybe simple to learn. So, and I suppose that in Russia, many universities now teach CUDA.
Oh,
so there are many.
Sounds great. Are you NVIDIA? There is a name for this. When universities are teaching CUDA technologies, NVIDIA gives them some kind of name. And are you in touch with NVIDIA, or are you just doing by yourself?
Yes, I am in touch with NVIDIA, with those people who are keeping they are keeping the university courses here. Maybe you know some of them, like Alexander Harlamov. No?
No, I'm in contact with the marketing team. I know a couple of people there.
Andrei Komisarov?
Maybe. No.
Okay. Okay, great.
I think Adnan means more that he knows more the USA NVIDIA.
Right.
Not Russian NVIDIA part.
Right. The people I know are from California.
But that is an interesting subject, Alexei. You can use TulaDev as a platform to give sometimes, the CUDA presentations, and this is a very high-level introductory presentation because we didn't know how deep is the audience in CUDA, but if there's an interest, we can perhaps discuss an opportunity to go a little bit more deep and do something.
Yeah, definitely. That will work. Yeah, we can think about it. I'm open for suggestions. And as I said, if there are many enthusiasts like you about doing GPU on NVIDIA technology, and then I believe you should open a HPC and supercomputing group like this thing, HPC and supercomputing group of something. Currently, it's going by state or city in US, but we have also Tokyo, and I think we have Sydney. And the good part is they're also sending lots of goodies like books and T-shirts or thumb drives or those kind of things you can give away to your friends or promote it there. Alright guys, any other questions? No more questions. Alright.
No question. Then I would like to thank our guest Adnan for giving the presentation on parallel thinking. Хочу поблагодарить Аднана за то, что он нашел время. На самом деле здесь, когда он начал презентацию, было 7 часов утра, то есть он очень рано проснулся, чтобы подготовиться и сделать презентацию, чтобы это не слишком поздно было. Поэтому мне очень приятно, что вот он смог найти такую возможность. И мы все, я думаю, очень благодарны ему за его презентацию подготовленную, поскольку он занимается этим на практике и вот делится с нами своими техническими навыками. So, thank you, Adnan.
Thank you, guys. Thank you. Have a great weekend.
Thank you.
Bye-bye.
Спасибо, ребята. До свидания.
До свидания.
Паш, я думаю, тогда ты можешь